Moving on to our problem number 4 here. This is, we have 2ty over t squared plus 1 minus 2t minus the value of 2 minus ln t squared plus 1 times the value of y prime. Now, as you can see here, there are no x, and that is replaced by t. So let's just replace all variables of x with t. Now we can see here that this is not our suitable form for exact differential equation. Now we have to rewrite this because it has to be m function of x of y plus n function of x of y dy over dx equals to 0. Since there is a minus sign here, we need to fix that. So we can rewrite this as 2ty all over t squared plus 1 minus 2t. That is our m. And we can turn this plus negative 2 plus ln of t squared plus 1 multiplied by y prime is equals to 0. Now this term here is our m. And this terms here is our n. Again, we have to check if they are equal. So partial derivative of our m with respect to y, or m of y, is equals to two ty all over t squared plus 1 minus 2t. Now, we can rewrite this as simply 2t over t squared plus 1 times y minus 2t. Since all of the variables t are constant, so since we are partially deriving this with respect to y, all of our t are constants. So therefore, our answer for this here is 2t over t squared plus 1. Now to get our value for the partial derivative of n with respect to x, or nx, that is partial derivative of negative 2 plus ln t squared plus 1. So as you can see, deriving ln u is simply du times 1 over u. So that's getting the derivative of our tn plus 1, then multiplying that to 1 over t squared plus 1. So that's, let me just rewrite that. So this is basically, if that's ln u, and like deriving that, that's du times 1 over u. So what's the derivative of t squared plus 1 with respect to x? Oh, sorry. We have to replace this with that is with respect to t. Now that is, so the derivative of t squared plus 1 with respect to t is 2t, and that's times 1 over t squared plus 1. Therefore, this is 2t over t squared plus 1. Therefore, our partial derivative of m with respect to y is equals to our partial derivative of n with respect to t. Therefore, this is an exact equation. And we can proceed. So you guys already know the drill. So the partial derivative of our psi with respect to t here, instead of x, it's with respect to t. That's basically psi of t. That's equals to our m, and our m is 2t y all over t squared plus 1 minus 2t. And in order to get our psi, we have to integrate this. So our psi is equals to, so in here, to integrate this 2ty over t squared plus 1, we can do a u substitution. So let's say our u is equals to 2 squared plus 1, and our du is equals to 2t. Now we can rewrite this as y, since our y is a constant because we are partial deriving with respect to t. So putting y outside, that's 2t over t squared plus 1 minus the derivative of 2t. So this is basically y squared integral of du over u minus t squared. Minus t squared. So the integral of du over u is ln u. So our psi is y ln u, which is our t squared plus 1 minus t squared plus h of y. Don't forget our h of y. Now next, to get our value for h of y, we need to partially derive this with respect to y. So partially deriving our psi with respect to y. So copy our value for psi, that's y ln t squared plus 1 minus t squared plus h of y. So since all of the t variables here are considered as constant, now we can rewrite this as simply, so the partial derivative of this is simply ln t squared plus 1. That's 1 is 0 because partial derivative of t squared with respect to y is 0 because it doesn't have any y. It's plus h prime of y. And we can equate this again to our n. And our value for n is negative 2 plus ln t squared plus 1. So simplifying this whole equation here, that's ln t squared plus 1 plus h prime of y. That's equals to negative 2 plus ln t squared plus 1. So we can cancel out our ln t squared plus 1 because it exists on both sides. Therefore, our h prime of y is equals to negative 2. Integrating both sides, we get h of y is equals to negative 2y. Now plugging that into our psi is y ln t squared plus 1 minus t squared plus h of y. And that is psi is equals to y ln t squared plus 1 minus t squared minus 2y. And our equation and our final equation is y ln t squared plus 1 minus t squared minus ty is equals to c. And that is our final answer. Now moving on to our last example for practice problems using exact differential equation. So we have here 3y cubed times e to the 3xy minus 1 plus 2y times e raised to the power of 3xy plus 3xy squared times e to the 3xy times y prime. Now this is our, this is our m, and this here is our n. Now again, we need to first verify if this is indeed an exact differential equation. So you guys already know what to do. We need to find the partial derivative of m with respect to y, or my. And that is 3y cubed times e to the 3xy minus 1. So as you can see here, in 3y cubed times e to the 3xy, it has two terms, so we need to use our product rule. So product rule is if simply the first term times the derivative of the second term plus the derivative of the first term times the second term. So this is 3y cubed times the derivative of e to the 3xy. That is, so if you can remember, the EU, the derivative of that is simply du times EU. So the derivative of 3xy with respect to y, that is 3x times e to the 3xy, then plus the derivative of our first term, which is 3y prime, that is 9y squared times e3xy. And yeah, that's it. Because here we have minus 1, but that is 0 because it does not have any y. So multiplying the terms, we have 9xy cubed times e3xy plus 9y squared times e3xy. Now next, we need to find the partial derivative of our n with respect to x, or our nx. And that is, writing down our value for n, 2y e3xy plus 3xy squared e3xy. So again, we have so in this case here, since we are partially deriving this with respect to x, so all of our y are constants. So for 2y times e raised to the power of 3xy, that is simply 2y times the derivative of 3xy, which with respect to x, that's 3y times e3xy, and plus. So we have here, supposedly you can see our term, the second term that we need to derive is 3xy squared times e to the 3xy. Now normally these are three different terms, but since we are partially deriving this with respect to x, our y is a constant. So let's just treat our 3xy squared as one term. So you know already the steps for the product rule. That's writing the first term times the derivative of the second term, then the derivative of the first term times the second term. So we have here 3xy squared times 3y times e raised to the power of 3xy. That's plus 3y squared times e raised to the power of 3xy. So simplifying all of this, 2y times 3y, that's 6y squared times e raised to the power of 3xy plus 9xy cubed times e raised to the power of 3xy plus 3y squared times e raised to the power of 3xy. Now since we have two terms that have the same exponential terms, we can just add them. So this is 9y squared e 3xy plus 9xy cubed times e to the power of 3xy. And this is equals to our my. So therefore, our partial derivative of m with respect to y is equals to our partial derivative of Rn with respect to x. Therefore, this is an exact equation. Now proceed. We have here the partial derivative of our psi with respect to x. That is basically our m. So our m is 3y cubed times e3xy minus 1. So you know what to do. Integrating both sides to get our psi. And our psi is okay. So for our psi here, so in here we can do a u substitution to solve for our equation. So let us say u is equals to 3xy. Our du is 3y because this is being derived with respect to x. So since our y is a constant, we can rewrite this as y squared times the integral of 3y times e to the 3xy minus integral of 1. So this is basically, sorry, wrong color. So this is basically psi y squared integral of du of eu minus x, because that's the integral of 1. Therefore, our psi is equals to y squared. So integral of eu du is simply eu. So our eu is e raised to the power of 3xy minus x. And don't forget our function h of y. So to get our value for h of y, we need to partially derive this with respect to y. So partial derivative of our psi with respect to y, and this is actually equals to psi of y. So that's y squared e to the 3xy minus x plus h of y. So here we are going to follow our product rule once more because we have two terms here, the y squared and our 3xy. And since both of them has y, so none of them are constants, we need to solve them. So that's writing our first term, y squared. Then the derivative of the second term, that with respect to y, that's 3x times e raised to the power of 3xy plus 2y times e3xy. Then that's plus h prime y. So this is 3xy squared times e3xy plus 2ye 3xy plus h prime of y. And of course, you guys already know, we can equate this to our n, because our n is equals to the partial derivative of psi with respect to y. So our n value is 2y e raised to the power of 3xy plus 3xy squared times e raised to the power of 3xy. So we can cancel out this term and that term because that exists in both sides. Therefore, our h prime of y is equals to 0. And and integrating both sides, we get h of y is equals to c. Therefore, going back to our original equation of psi, which is y squared times e raised to the power of 3xy minus x plus, this is supposed to be blue. Y squared times e to the 3xy minus x plus h of y. That is psi y squared times e 3xy minus x plus c. Therefore, our final answer is y squared times e 3xy minus x is equals to c. And this is our final answer. So I hope you guys now know how to solve the solutions for differential equations that are exact. So I guess that's all. See you guys next time.